Okay, so we are talking about equivalence relation. So we will discuss more on that. So, so just to recap, so what is the equivalence relation? Suppose let S be a non-empty set. Then we know that binary relation is basically a subset of the Cartesian product. Any subset of the Cartesian product is a relation. Now we call this relation to be equivalence relation if it is reflexive. That means if A is belongs to rho for all A, symmetric. That means if A B is belongs to rho, then this must imply B A is belongs to rho, and this must be true for all A B. Whenever A B is belongs to rho, then B A must belongs to rho, and then transitive. So, if we have A B belongs to rho and B C belongs to rho, then this must imply A C belongs to rho, and this must true for all such A B C. Now, if all these three satisfy, then the relation rho is called equivalence relation. Rho is called an equivalence relation. Okay. So, we have discussed some example of the equivalence relation in the last class. So, now we will talk about the equivalence classes. We define the equivalence classes on this non-empty set S. So, suppose we have a set S which is non-empty, and we have equivalence relation on this. Equivalence relation on this. Okay. So, now we define equivalence classes. Let A be any element. We take an element from S. So, this is our S. We take an element from S A. Okay. Now, we define the class. This is this way, or we can write this way. Any one of this way, class of A. Okay, this is nothing but this is the set of all B from A such that A is related with B. That means A B belongs to rho, and this is equivalence. So, same as B A belongs to rho. A B belongs to rho. So, this class, that means this is the class of all the elements B which are related with A. So, we follow one notation this way. Okay. So, box is another notation in the integer, which is the integral part. So, anyway, these two are different notation. I mean, if there is any confusion, you can use CLA, class of A. Okay. So, this is the class of A. This is the set of all element B such that A is related to B. Okay. Now, this class is non-empty. So, this we can claim CL of A is non-empty. There must be at least one element in this class. Why this is non-empty? Why there has to be one element? Who is the element? A is the element, because this is a reflexive. This relation is reflexive. So, A must be belongs to rho. So, that means A is always in this class. So, there is at least one element A. So, that means it is non-empty. These classes are always non-empty. Okay. So, now we will have some result on this class. So, this is the first result, this class is non-empty. Now, another result is, so if we take two elements A and another element B. Now, if you consider the class of A, class of B. Okay. Now, the theorem is telling either class of A is same as class of B or they are disjoint. So, that means this type of situation will not occur. This is a class of A, this is class of B. This is not possible. So, either one of these, either this will happen, either these two classes are same or these two classes are different. I mean sorry, this is empty set. Either they are these two sets are same or they are these two sets are empty. Okay. So, how to prove that? Okay. So, this is true for any A B. So, this is true for any A B. So, how to prove that? So, to prove this, so A B belongs to S cross S. Now, if A B belongs to S cross S, that means there are two possibilities, A B either belongs to rho or A B does not belongs to rho. Now, if A B belongs to rho, so that means this case, then we have this one, we will prove that, and if A B does not belongs to rho, then they have two disjoint class, they will not have any common element in the class. So, that we have to prove. Let us prove the first one. So, the case 1, if A B belongs to rho, then our claim is their class is same, then class of A is basically same as class of B. Then we need to prove that class of A is basically class of B. And so, this how to prove this? Okay. So, how to prove these two classes are same? So, for that we need to search, these are basically sets. So, for that this must be a subset of this and that must be a subset of this. So, let us try to prove this one, class of A is a subset of class of B. So, for that we need to take an element from here, let x belongs to class of A. Then we have to prove that x belongs to class of B. So, x belongs to class of A means what? X belongs to class of A means A is related with x. That is the definition of class of A. Class of A is a consist of. Now, if this is so that means A x belongs to rho. So, now this means x A belongs to rho because symmetric property of rho, and we know this A B belongs to rho, we know. So, and also we know A B belongs to rho. Okay, now, these two both give us x A belongs to rho, sorry x B, because of transitivity property, because rho is symmetric equivalence. So, it is the transitivity property, So, that means x belongs to x belongs to class of B. So, if you take a element from class of A, it is an element of class of B, and this is happening because A B are related. Similarly, we can prove this is a subset of this. We have to take y from here and then we have to show this y is belongs to this. So, that means, so this is the so the other way, let us try to prove that. very similar way. So, now we need to show that class of B is a subset of class of A. Now, how to prove that? Let y belongs to class of B. So, that means y and B are related. So, this means B y is related, this is by the property of symmetricity, symmetric, and we know that A B is related, sorry y B, y B is related, y B is related, we do not need this symmetricity property to use, y B is related, and we know that A B is related, that means B A is also related, because rho is symmetric. Now, from these two we can say y A is related because of transitivity property. If y is related means y belongs to class of A. So, that means these two are same. So, class of A and class of B are same basically, if we take two elements which are related. So, this is one observation. Another observation is, if they are not related, if we take 2 point A B, 2 element and they are not related, then their class is disjoint. So, that means, if we take A and if we take so this is the class of A, and if we take another element B which is related with this A, then class of B is same as class of A. So, this is class of A which is same as class of B, and if we take another element C which is same as class of C, like this. So, they are basically give us the same subset. Okay. So, now the another part. So, if we take two element A B which are not related, if A B is not related, that means A is not related to B, then we have to show they cannot have a common element. Then we have to show this class of A and class of B is disjoint, they have no common element. So, this is the second part of the theorem. So, how to prove this? So, let us try that by using the contradiction method. Suppose they are non-empty, they are not empty. Suppose, if possible, suppose class of A and class of B is not an empty set. So, that means, this implies there exists an element x, this is the symbol for there exists. There exists an element x which is the which is in the intersection, and we need to arrive to a contradiction. And here we know that A B is not related, A B does not belongs to rho, that is that information we have. Okay. So, now so now this implies what? X belongs to class of A and also X belongs to class of B. Now, X belongs to class of A means what? X and A are related and X belongs to class of B means what? X and B are related. Okay. Now, this imply by the symmetric property we can say A x belongs to rho, this is by symmetricity, because rho is equivalence relation. So, rho is symmetric also, and x b belongs to rho. Now, this x a belongs to rho, x b belongs to rho, and rho is equivalence, that means rho is transitive also. So, if rho is transitive, then these two will give us what? A b belongs to rho, since rho is transitive. but that is not possible. We already assume A B is not belongs to rho, which is a contradiction. Which is a contradiction against our assumption that they are not empty, contradiction, which is a contradiction. Hence, our assumption is false. Hence, if they are not related, then the class of A and class of B is having no common element. So, this implies class of A, class of B is empty set. Okay. So, in other words, if we this is our S, if we take two element A B which are not related, then this if this is the class of A, this is the class of B. They will have no common element, because once they have a common element, then they has to be in the same class. And they are so all the elements over here which are related, they have a same class with this, they have a same class with this. So, this will give us an idea of the partition. Okay. So, we just rewrite this theorem which we have proved just now. So, let us just rewrite this theorem in a proper way. This is telling that is the statement of the theorem. Let rho be an equivalence relations, rho be an equivalence relation over a non-empty set S on a non-empty set S, and if you take any two element from S, then either class of A is equal to class of B, either one of these two, or class of A intersection class of B will be empty. So, that means that depending on this will be the case when A is related to B, and this will be the case when A is not related to B. So, if A B are any two element, then A B will be belongs to Cartesian product. Now, rho is a subset of the Cartesian product. So, this is a this is there are two possibilities, either it is belongs to rho or it does not belongs to rho. If it is belongs to rho, then this will be this case, and if it is not in rho, then this will be the this case. So, just now we have proved this theorem. So, now this is theorem telling us a partition on the set S, because this is giving us the disjoint classes, right. So, these disjoint classes will give us basically a partition on this set S. Now, if S is finite, it will be a finite, I mean it may give us a finite partition or infinite partition depending on the relation. We will take an example. So, basically this we will have a proper statement of this theorem, but roughly this rho, which is an equivalent relation, rho gives a partition on S. So, this is our S. So, how it will give us a partition? Just the theorem, we take an element and we consider all the this is A. So, this is the class of A. So, this belongs to all the elements which are basically related with A, and then we take another element which is not related with A, say this is A1, we take another element A2 which is not related with A. If it is related with A, it will be in the same class, they will perform the same class. This is class of A2, then we take another element A3 which is not related to A1 and A3. So, this will be C3 like this. and they are disjoint. So, eventually they will give us a partition, because partition means it is a collection of disjoint subsets whose union is the whole set, because it is just a. So, basically S will be written as union of this class of A, where A belongs to S. Okay. So, this will give us the partition, and the converse is also true. Converse is also true, that means, if we have a partition, then we can have a equivalence relation. We will have that, but before that let us take an example of this, how to get these partitions, a real life example on the integer set. Okay, so, that will give us basically the, we are going to define the Zn. Okay. So, this is an example of such partition. So, let us take the set Z. This is the set of all integers, we know, set of all integers. Okay. Now, we define, we take an integer, let n, it could be 5, anything. I mean, usually we take this to be maybe positive integer, or it could be negative integer also, but let us first take some positive integer. Okay. Now, we define a relation rho, which is basically, we take two point a b, two integer. Now, they will be related under rho if a minus b is divisible by n. So, that means n divides a minus b. So, that means what? That means, if a is an integer, then a mod n. A mod n means what? So, we divide a by n, then this will be the remainder basically. If this is same as b mod n, suppose for example, if n is say 5, suppose n is 5. Now, if you take a to be 16, so what is a mod n? A mod n is basically 1, because 16 mod 5, it is 1, remainder will be 1. And if we take say 21, b is 21 say, then also b mod 5 is 1, and also we can check by this way also. What is a minus b? A minus b is basically just the minus 5, which is divisible by 5. So, that means, if we take any two integer a b, and if we divide by, try to divide by n both the integer, if the remainder is same, then they are related under this relation rho. This is called congruence relation. This relation has a symbol, this is called congruence, modulo congruence mod n. This is called congruence relation. That means, very simple way, we take two element a b, two integer a b. Now, if we try to divide a by n, we get a remainder, it may be 0 also, if it is divisible, a is divisible by n, and we try to divide b by n, and if they belongs to the, if the remainder is same, then they are related under this relation. This is called congruence relation. Okay. So, now this is basically, we have seen this is an equivalence relation, or we can just prove that this is an equivalence relation. Now, if this is an equivalence relation, then it will give us equivalence classes. So, who are those classes basically? So, classes is basically the remainders all possible remainders. So, that is very interesting to see these classes. So, these classes are basically we have this set of integer z. Now, we have a number n. Now, we divide the integer, there will be remainder are like this. So, 0 class, 1 class, 2 class like this. So, n minus 1 class, because if we divide any integer by n, there are these possibilities are there, but if n is equal to 5 say, n is equal to 5 means, so there are possibilities is 0 class means all the elements like 5, 10, minus 5, 15. So, all these are in 0 class, that means they are all related under this relation, and then we have 1 class dot 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 we have up to 4 class, because if we divide it by 5 there are this many remainder 0, 1, 2, 4. So, this collection, this set is called Zn. So, 0 class, 1 class and n minus 1. This is called Zn, this class are called Zn. So, what is Z5? Z5 is nothing but there are 4 classes, class 0, class 1, class 2, class 3 and class 4. So, which are in class 1? Class 1 means these are the elements, say 6, 16, 11, because all they are related under this relation that phi a row, and they have, if their remainder is 1. So, these classes are basically this Z5. Okay. Now, in general if it is n, so there are 0 to n minus 1. So, n class. Okay. This is the way how we define the Zn. Now, the theorem has another part. This is an example of the equivalence classes. This is how we define the Zn, integer modulo n. Now, the theorem has another part. It is telling, suppose S as a partition, disjoint partition, then there exists an, then we can have a, then there exists a equivalence relation rho. Equivalence relation rho. So, how to show this? Suppose we have a partition, P is a partition, this is S, P is a partition say S1, S2 like this. So, we defined AB belongs to rho if AB belongs to the same class, same subset. Partition is a subset, disjoint subset. AB belongs to rho if and only if they are in the same subset. Then we can show this is equivalence relation, because AA belongs to rho. If AB belongs to rho, then BA belongs to rho. If AB belongs to rho, BC belongs to rho, then AC belongs to rho. So, this is the other way, other part of this theorem. Thank you.